In this talk, I'm going to talk about the full self-consistent implementation of the local self-interaction correction method. Local self-interaction correction, or the LSIC method, is a new SIC method that appeared in 2019. And up until now, the LSIC application was done using the perturbative energy evaluation using the PGSIC density or the so-called quasi-SCF approach. And what is new in this talk is the full self-consistent implementation part. This was the work that was done in the 2020 and 2021, and this is something we promised to deliver during this funding period. So there it is. In this slide, I compiled a short history of the LSIC related publication work, only showing the first author to save space. The original LSIC work, we started working on this project in the beginning of the 2019, and some of the people in the FLOSIC community may remember the talk by the Professor Zope. He gave the talk on the original LSIC work at the FLOSIC All Hands meeting in the August of 2019. And that work was eventually published by the end of that year. And because of the very good performance of the LSIC, the article was picked up as the JCP Journal of Chemical Physics Editor's Choice articles of 2019. And also this work was featured and received the DOE highlight. And you can find the web article on the DOE website. And since then, several follow-up works and LSIC applications work were done and published in here. And I'm going to pick some of the highlights of those articles. So when you apply the LSIC to the static dipole polarizability properties, LSIC shows the remarkable performance, and that's the polarizability for the water, polythene, and the molecules. And the LSIC shows the improved performance over both DFA as well as over the PGSIC. And for other properties such as the reaction barrier height and exchange coupling constant prediction, this work was done by the Prakash. Although LSIC performance was not remarkable, nevertheless you saw the noticeable improvement for the LSIC performance over the PGSIC. One of the exceptions for the LSIC was the water cluster binding energy. But we have the understanding of why LSIC doesn't perform well for the water cluster binding energy. And the discussion can be found in the Selim's LSIC with the simple scaling factor paper in the 2020. While we were preparing the manuscript for the publication for some of the work listed in the previous slide, one of the major concern/comment/criticism we received from the referee was the following. Why is this method not variationally implemented? And on one hand, the referees has the point because some of the scientists may consider if it's not variational, it's useless. But on the other hand, back then we didn't have the full variational implementation of the LSIC, but we still need to convince the editors and referees to get our work published. So we made two of the arguments to convince the editors and referees. And here are the two of them. So the one argument we made was, although we used the perturbative calculation, the one-shot calculation of LSIC, we didn't perform the one-shot calculation using the DFA density, but instead we performed the one-shot calculation using the PGSIC densities. So the density we used already has the self-interaction correction effect included at the level of the PGSIC theory. So using the PGSIC density should be more accurate than simply using the DFA density. That's the one argument we made. The second argument we made was we can roughly estimate the effect of the self-consistency for LSIC by comparing the full SCF calculation and the non-SCF calculation for the orbital scaling by the Bidulph-Kucerius approach. Because early on the stage, we had the full SCF implementation for the orbital scaling ready in the FLOSIC code. And we compared the performance difference for the non-SCF versus full SCF, and performance differences were small. So we argued that for the LSIC, we also see the similar amount of the difference between the non-SCF versus the SCF. Those were the two arguments we made at that time. But having said that, to get the full understanding, complete understanding of the LSIC method, the full SCF implementation is necessary. And since now we have the full SCF implementation of the LSIC, we can actually study and see if those arguments we made previously were valid or not. And we can also grasp the good understanding of how LSIC method works. This is the LSIC energy equation. So those equations, the first line of this equation is very similar to what you see for the PZ, Purdue-Zanger SIC approach. So you take the DFA exchange correlation energy and you subtract the self-Hartree energy and self-exchange correlation energy for each and every occupied orbital. Very similar to the PZSIC energy. In case of the LSIC, for the self-Hartree energy and self-correlation energy, when you write those integral, you place the local scaling factor z of sigma inside of the integral for each of those terms. So what this z does is the following. This quantity will adjust the amount of the self-interaction collections point-wise in space. So some of the point where the self-interaction is correct, this scaling factor will apply the full effect of the SIC, while the other places where you don't need much self-interaction collections, this z will scale it down to make it not so much collections. So in case of the LSIC, the collection is done by point-wise in space according to the quantity of z. Let's go over the terminology. So we use the terminology, the PGSIC or the orbital SIC or the LSIC accordingly as what energy equation we used. So if you use the LSIC equation like this, we call it LSIC. If we use the orbital scaling equation by Bidulph-Kucerius, we'll call it the OSIC. And if the energy equation is the Purdue-Zanger SIC, we will call it the PGSIC. As for the scaling factor, we will use the terminology internal scaling, external scaling, and the global scaling accordingly as the way you place the scaling factor. So if you place the scaling factor like what you see in the LSIC equation here, because the scaling factor is placed inside of the integral, we will refer this as the internal scaling. If the scaling factor is outside of the integral, then we will call it external scaling. The global scaling is for the case where the scaling constant is the scaling factor is constant. Now, any of those SIC methods, you can implement those with your choice of the local orbital. So here, in the scope of this talk, if the implementation, any of those SIC implementations were done using the flow implementation, we will refer it as the FLOSIC, the Fermi loading orbital self-interaction collection. And in this talk, we will consider implementing the full SCF for the LSIC LSTA functional with the local scaling factor or the isoorbital indicator of the Z equals to the Weizsäcker kinetic energy density over the total kinetic energy density. And this is because in the FLOSIC code, some of the functionals are implemented differently. So the MetaGJ functional and the functionals from the libxc functional library, those uses the integration by parts. So the derivation for the full variational implementation will be different for those cases. Similarly, because in the full SCF, you have to take the variation of the scaling factor. So depending on your choice of the local scaling factor, your mathematical derivation will be different. So in this talk, we will focus this particular set of the functional and the scaling factor. Okay, so one of the important things to mention for the LSIC functional is that the LSIC functional is functional of not only the local orbital, but also it is a functional of the canonical orbital as well. And to take the variation with respect to rho, you need to consider both the local orbital and canonical orbital. And to go from the one set of the orbitals to the other set of the orbital, you have to apply the functional chain rule like this. So by applying the chain rule like this, you can go from the delta rho to the delta rho I. And to relate the one set of the orbital to the other, in the case of the flow, we have the relationship like this. So if you sum over all of the local orbital, those needs to sum up to the canonical orbital, we can use that relationship to relate the one set of the orbital to the other set of the orbital. This type of the chain rule is also done for the orbital scaling by the Bidulph and Scuseria. You can see it is used in their supplementary information of those papers. Okay, now let's start taking the variation for the LSIC energy term, starting from the self-exchange correlation term. So this slide is the textbook example of how you take the variation of the energy functional. We took the variation of the rho. So here the small variation, the epsilon phi, is introduced to the rho. And if you work your math way down, you eventually obtain this expression, the delta of the EXC for the LSIC with respect to the delta rho. And in case of the self-exchange correlation term, you have the two terms. The first term is the scaling factor times the exchange correlation potential. And second term is the variation of the scaling factor times the exchange correlation energy density. Now, when you go back to the original full SCF implementation of the FLOSIC methodology in the 2017 paper, to obtain the SIC potential, what they did in this paper is you take the delta of the rho and then set the rho evaluated at the flow to obtain the SIC, the orbital potential. So in our case, we also follow the same procedure. Here we took the delta of rho and later we set the rho at the flow to get the SIC potential. Now moving on to the self-Coulomb term. You can follow the same mathematical procedure for the LSIC self-Coulomb term. And if you work the math down, eventually you get the expression like this. So in case of the self-Coulomb term, you obtain the three terms. The first term looks like the Coulomb potential, except that in this case, the scaling factor is sitting inside of the integral. So for the convenience, we will refer these terms as the scaled Coulomb term in the scope of this talk. And the second term is the scaling factor multiplied with the Coulomb potential. The third term is the variation of the scaling factor times the Coulomb energy densities. And you get those three terms. Combining those self-exchange correlation and self-Coulomb terms, you get the variation of the LSIC energy with respect to the rho. And you obtain those 6 terms. The first term is the DFA potential. The second term is the scaled Coulomb term. And third and fourth terms are the scaling factor times the PGSIC potentials. One for the Coulomb and one for the exchange correlation. And the fifth and sixth terms are the variation of the scaling factor times the PGSIC energy density terms. So you obtain those 6 terms. To quickly check this expression, you can do so by taking the limit for the scaling factor. So if you let the scaling factor goes to 1 everywhere, it should reduce down to the PGSIC expression. So let's do that. And if you do that, the term number 5 and number 6 drops out, and the term number 2, 3, and 4 essentially reduce to the self-Coulomb and self-exchange correlation terms from the PGSIC, and it correctly reduces down to the PGSIC in that particular limit. Similarly, if you take the limit where the z scaling factor goes to 0 everywhere, all of the terms drops out except the DFA terms. So in this limit, once again, it gives the correct limit of the DFA. So this expression seems valid for those 2 limits. In terms of the difficulty of implementing those terms, term number 1 is given, and term number 3 and 4 are relatively easy to implement. You simply need to multiply the scaling factor and the PGSIC potential for those terms. So those are the easy term. And term number 5 and number 6, those 2 guys have the variation of the scaling factor. And those have the moderate difficulties. But inside of the FLOSIC code, we already have tools to do so. So those are moderate difficulties. And the real challenge of implementing the full SCF LSIC into the FLOSIC code is actually coming from the term number 2, scaled Coulomb term. And we will talk about this term in next slides. Okay, let's take a second and talk about the quasi-CF. In the LSIC, we apply the local scaling to the PGSIC energy densities. Now, you can follow the same spirit, and instead of the scaling down the energy density, you can scale down the PGSIC potential. If you do that, you get this potential expression in the bottom. And for here, we will refer the method using this potential expression as the quasi-SCF. Now, the one potential problem is that you don't know the exact expression for the energy that corresponds to this potential. So that's the one potential problem. In our group, at one point, we attempted to apply the Levy-Perdue theorem to obtain the energy that directly corresponds to this expression, but we didn't pursue that approach only because LSIC energy LSIC energy expression was working really well. But that's something we attempted at one point. Now, if you want to get the mathematical connection between this quasi-SCF expression to the full variational LSIC energy expression, you can also do so. So if you drop out all of the variation of the scaling factor terms, drop out term number 5 and 6, and if you approximate the second term by taking out the scaling factor outside, you essentially in those conditions, both of the the above equation reduced to the quasi-SCF. So there is some mathematical connection between the two as well. Now let's go back to the above equation and let's look at the those implementation. Okay, to solve the term number 5 and number 6, those guys have the variation of the scaling factor, delta z, delta rho. And this expression is very similar to how the local hybrid functionals are implemented. So we can follow the same procedure as the local hybrid, and you can write the matrix element corresponds to this potential as like this. Now, although this expression seems intimidating, but it shouldn't be, because when you run the meta-GGA calculation using the FLOSIC code, you actually do something very similar to it. So inside of the FLOSIC code, the SIC meta-GGA calculation is implemented using this expression. It also uses the integration by parts like this. And what changes from the meta-GGA to the LSIC expression is what's shown in the red big box. So what we needed to do was modify what goes inside of those integral terms. And we can use the similar approach as how we implemented the SIC meta-GGA in the FLOSIC code. And although the LSIC right now is done at the LDA level, you still need to do this type of the operation, and that is because the scaling factor we used has the dependency on the not only the density but also the gradient of density and the kinetic energy density. So that's the reason we have to do it this way. Now the one last term, the second term, the scaled Coulomb term, implementing this in the FLOSIC code is very difficult. So inside of the FLOSIC code, the Coulomb energy and Coulomb potentials are obtained using the subroutine called Coupot1. And as long as you are modifying the output of the Coupot1, that's doable. But modifying what goes inside, modifying the inside of the Coupot1 subroutine is very challenging and very difficult. So for the implementing the full SCF for the LSIC, we took a different approach. Instead of using the analytical Coulomb, we decided to use the numerical Poisson solver to deal with this second term. Now, in the previous talk by Dr. Chen, he talked about the numerical Poisson solver in the FLOSIC seminar talk in the January of the 2022. And so I will skip the technical details. The basic idea of the numerical Coulomb solver is following. Instead of solving the Coulomb potential analytically, the numerical solver takes the density, electron density as an input and computes the Coulomb potential that corresponds to the inputted density. And this is very useful for the obtaining this scaled Coulomb term, because to obtain this term, all you have to do is, instead of sending the rho as an input, you can send the rho times the scaling factor as an input to obtain the scaled Coulomb term like this. So by using the numerical Coulomb solver, numerical Poisson solver, it simplifies dramatically for obtaining this particular challenging term otherwise. And this work of the numerical Poisson solver, the manuscript was submitted to the Journal of Chemical Physics for the publication at this stage. Okay, so that gives all of the term we needed for running the full SCF LSIC calculation. But let's go over a few more slides for the additional stuff, additional things. So one of the things is the FOD force. You need FOD force to optimize the FOD in the FLOSIC calculation. In the original article about the FOD forces, you can express the FOD force for the PGSIC calculation like this. And what is important here is that you can express this force in terms of the SIC matrix. When we implemented the MetaGGA PGSIC into the FLOSIC code, what we did back then to obtain the FOD force for the MetaGGA case was substituting this SIC matrix with the MetaGGA equivalent matrix element to obtain that. And we did compare the force obtained by replacing that way against the finite difference and saw the agreement. For the completeness, by doing this type of the substitution, you might need additional terms for the completeness because the MetaGGA SIC matrix, the blah and ket are not same as this. But in the practical use, because we ran the test and saw the agreement of the forces from this way against the finite difference, in the practical use, doing this is fine. Replacing this term is fine to obtain the FOD force. In case of the LSIC, we also modified the SIC matrix similar to modification done in the MetaGGA, SIC MetaGGA. We also replace this term with the LSIC SIC matrix equivalent to obtain the force. And that allows us to optimize the FOD at the LSIC level of theory. The next one is the atomic force. The atomic force or the Poulet force is used for the optimizing the nuclear coordinate as well as the FOD coordinate simultaneously. And this expression of the Poulet force this work was done by the Kai Trepe in the 2019 for the PGSIC LTA. Okay, and in case of the LSIC, you need to modify those two terms. So here the capital lambda ij is the difference of the Lagrange multiplier matrix term, the lambda ij minus lambda ji. So if you update the SIC matrix in the LSIC, this term will be automatically updated accordingly. And this term over here is similar to the DFA SIC Hamiltonian, but you need to take a derivative with respect to the nuclear coordinate. So we did that this derivative of the nuclear coordinate, and we implemented into the LSIC code. So we also have the Poulet force implementation in our LSIC implementation. And using this Poulet force to optimize the FODs and the nuclear coordinates simultaneously, it works in principle, but in the practical use, we need to be a little bit careful to run. And that's because you may end up with the metastable state that you didn't intend to get there if you use this approach. That's the potential caveat. And you can look at this problem as this problem by thinking about the dissociation energy for the dimer. Here, this is the NaCl dimer. This plot was done using the PZSIC LDA level of theory. So in case of the dissociation energy for the NaCl, you can prepare the initial FOD as Na plus and the Cl minus, and you can get the blue solid line like this. And you can repeat the same thing, but instead now you can prepare the initial FOD as the Na and the Cl, and you can get this dashed line. So depending on how you prepare your initial FOD, you get those two different lines. Now in this case, you can tell which curve is which because of how you prepared your initial FOD. But when you are optimizing the nuclear coordinate and FOD coordinate simultaneously, it becomes much more harder to tell what is happening for that calculation. So that is something you need to be careful when you decided to use the play force to get the FODs and the nuclear coordinate. But otherwise, this approach also works. Okay, one final slide about the everything else. We have a LSIC full SCF implementation of the LSIC, and right now we have a serial code ready for the calculation. With this code, you can run the SCF, and you can also get the FOD force, and you can optimize the FOD at the LSIC level of theory. The first thing we did was we took the FLOSIC code and replaced all of the analytical Coulomb routine with the numerical Coulomb solver routine. And we actually checked that everything works at that stage and proceeded with the implementing the rest of the LSIC terms. For the LSIC calculation, you need the both scaled Coulomb terms, and also you also need the unscaled Coulomb term. So you have to run the Coulomb subroutine twice to get each of these guys. So this is potential downside in terms of the computational cost. And for the LSIC LDA, the either potential mixing or Hamiltonian mixing can be used. This is because although the SIC Hamiltonian term for the LSIC contains the meta-GJ-like expressions, what is being mixed inside of the FLOSIC code is the DFA term only. So you can either mix the DFA potentials or the DFA harm that you can do it for the LSIC LDA. Now, here is the result. So we did the performance comparison for the LSIC one-shot against the SCF. For some cases, we also chose the quasi-SCF and the SCF with the FOD optimization. So now let's look at the result. This is the total energy of the atoms. We run the calculation and compares the energy against the accurate reference values by Chakraborty's. So closer to the zero, that's the good performance. And here we run the LSIC one-shot calculation and the LSIC SCF, and we also run the LSIC with the FOD optimization. So we run those three sets of the LSIC calculation. And visually, those three sets of the LSIC performance are very similar. They are almost on top of each other. And this one is the close-up view of the black box like here. And when you close up, you see some difference. So going from the one-shot calculation to the SCF, you see the energy decrease, slight energy decreases. How much? On average, that this energy decrease is the 2.42 millihartry. And similarly, going from the SCF to the FOD optimization, the energy goes down even further. The energy goes down from the SCF to the FOD optimized by the average of the 1.66 millihartry. That's what we saw for the atom total energies. And in this slide, we are showing the atomization energy performance using the AE6. And down here is the reaction barrier height calculation using BH6. What's shown here is the error with respect to the reference values provided by those database. So visually going from the one-shot blue to the SCF orange to the FOD optimized green, visually you can see the performance are very similar from the blues to the orange to the green. And when you look at the mean absolute error, the one-shot mean absolute error is this much, and the SCF and FOD optimizations are this much. So they are very close to one another. Here we also looked at the quasi-SCF implementation. In case of the quasi-SCF, you see some difference compared to the rest. And in fact, the quasi-SCF gave the decrease in the mean absolute error compared to the other. As for the energy shift, of the molecules from the one shot to the SCF, we saw the fairly the uniform energy shift from the one shot to the SCF. They are somewhere between the -2.2 to the -6.3 kcal per mole. On the other hand, the energy shift for the quasi-SCF from the one shot to the quasi-SCF, they were different. In this case, the energy shift was positive 5.5 to the 32.1 kcal per mole. And we saw that for the quasi-SCF, the larger molecule seems to experience larger energy shift. So the plus 32.1 energy shift is coming from the C4H8. And you see the smaller energy shift for the smaller system. So we think that this difference of the energy shift depending on the system size is contributing the decrease of the mean absolute error for the quasi-SCF. Now let's look at the barrier height performance. So although you see some difference depending on the reactions, the overall mean absolute error from the one shot to the SCF to the FOD optimized, they are very similar performance, the less than the 1 kcal per mole difference. And in this case, quasi-SCF also shows the very good performance. And overall, all four cases, the performance are close to each other. In this slide, I'm showing you the HOMO eigenvalues obtained from the calculation. Here, the negative of the HOMO eigenvalues compared against the experimental ionization energies taken from the NIST database. And here we included the scan and PBE as a reference or the representative for the DFA. And the scan and PBE, those two DFA cases, the HOMO eigenvalues are underestimated notably. And when you apply the PGSIC, the PGSIC LDA results are those black circles. The HOMO eigenvalues are pushed up like this. And this is because the PGSIC makes the exchange correlation potential deeper. And as a result, you see this improvement in the HOMO eigenvalues here. But you can also see those PGSIC values are slightly overestimated. When you apply the LSIC, what we got was those red data points. And from the PGSIC, the mean absolute error was 2.1 electron volt. And the LSIC, the mean absolute error decreased to the 1.04 electron volt. So you see the decrease in the error. There. Okay, we also looked at the quasi-SCF for the HOMO eigenvalues, And in this case, when you apply the quasi-SCF, what we obtained was those blue triangle data points. And visually, you can see that quasi-SCF performance are very good compared to the other method. So interestingly, the quasi-SCF mean absolute error is the 0.77, the smallest among data point, the method we used in this slide. Okay, in this slide, we are showing you the bond length using those 5 methods. Here, we obtained the bond length and compared against the CCSD estimate. And for determining the bond length, we computed the 6 to 8 point energy evaluation near the experimentally reported bond length values. So those are the experimental value plus minus 0.5 bores up to the plus 0.3 bores. And we fitted those data points using the polynomial fittings to determine the minima of that energy curve. As the fitting function, we used this polynomial function as a fitting function. And this term, this function includes the order of 3 terms in addition to the parabolic term. And this is because by including this order 3 terms, we found that the fitting error is smaller than just by using the parabolic term only. And I think by including this 3rd order term, it captures a slight skewness of the curve, and hence it gives the better fitting than the parabolic. So we use this function to get the minima of the energy curve to obtain the bond length. Now, this is what we saw for the LSIC calculation. Right. Okay, but before that, in case of the PZ-SIC is known to find the bond length to be too short. So in case of those dimers, those 7 dimers, PZSIC, LDA, they are all underestimated. And when you apply the LSIC, the bond lengths are in general slightly overestimated. And we looked at applying the SCF and also performing the FOD optimization. They didn't change the overall performance from the one-shot calculation. The only exception is the lithium nitride. In this case, using the SCF and FOD optimization lowers the bond length. But otherwise, we didn't see noticeable difference from the one-shot calculation. And finally, the water cluster binding energy. We computed the binding energy of the water clusters. This one is shown in the milli-electron volt per water molecules. And we compared that value against the CCSDT energy, the CCSDT values. And this is what we found. So again, closer to the 0 is the better, and PBE actually does a really good performance. And the PZSIC at the LDA level underestimate quite significantly. And one-shot calculation, as previously we found, and the discussion is done in the Selim's paper, the LSIC using this particular scaling factor Z overestimates the water cluster binding energy quite significantly. And this is one place where the LSIC performed really poorly. When we apply the full SCF, their performance remained very similar. Not significant change was seen for this case. So there's no apparent difference from the one-shot to the full SCF using the LSIC with D. But we already know why this happens, and as we understood, this is because the limitation of the isoorbital indicator, because this particular isoorbital indicator cannot tell the weak interaction region. And also the another reason is the functional itself. The LDA is also a poor functional for determining the weak interaction. So those are two combinations why the LSIC with Z doesn't perform well. And we previously, when we swapped the scaling factor from the Z's to the ratio of the density, the rho I, the orbital density, to the total density, we found the data point like this. So you see, just by swapping the isoorbital indicator, we saw the significant improvement for the water cluster binding energy. So this performance is similar to, slightly worse, but similar to the scan performance. And what this is telling us is that to improve the LSIC method further, we need to investigate and improve the quality of the isoorbital indicator, or either that or tune the functionals to perform better for this case. Here is my summary. So in this work, we worked on implementing the full SCF of the LSIC method, and we succeeded. The SCF LSIC maintains good performance, energetic performance of the one-shot LSIC. And finding of this supports the previous studies of the LSIC using the PGSIC densities. It also tells us that for the energetic performance, using the PGSIC LSIC with the PGSIC density is a good alternative to running the full SCF calculation. And when we looked at the energy shift from the one-shot to the full SCF, the energy shift for that case is fairly uniform. They are usually in order of the millihartry or in a few kilocal per mole for both atoms and molecules. When we looked at the quasi-SCF implementation, energy shift for the quasi-SCF, on the other hand, they are not uniform. So the larger system experienced more energy shift, and smaller system seems to have the smaller energy shift. For some cases, the quasi-SCF may be a very good alternative to the full SCF. That's what we saw for the HOMO Eigenvalues. And we saw decrease in the mean absolute error for the atomization energy. So that may be the case. Now this and those are the contributor for the LSIC project from the UTEP group. And this is our group picture before the pandemic. Thank you for your attention and have a scientific day.